Welcome back to The Explainer. Today, we're diving straight into one of the most stubborn, frustrating roadblocks in modern medicine, the black box problem of artificial intelligence. Now, we've all heard the hype, right? How AI is poised to absolutely revolutionize healthcare. But, well, there's a massive catch. When a deep neural network spits out a medical diagnosis, it almost never tells you how it actually got there. It is a total black box. And in a field where literal lives hang in the balance, doctors are understandably pretty hesitant to just blindly trust an unexplainable machine. But what if we could cure this black box problem? What if instead of just throwing millions of raw images at an AI and crossing our fingers, we could literally fuse human medical expertise with machine learning? Let's dive in and unpack a groundbreaking study that does exactly that. So, here's the big question. Can we actually teach an AI to think like a cardiologist? The stakes here are incredibly high. I mean, picture this. A patient comes into the ER with a really rare heart condition. A human cardiologist relies on years of grueling medical school, deep anatomical knowledge, and honestly, a bit of intuition to spot that subtle anomaly on the monitor. Traditional AI, on the other hand, relies entirely on data. Massive amounts of data. So if a disease is rare, the AI simply hasn't seen enough examples to know what to look for. Basically, it fails exactly when we need it the most. Section 1. The AI healthcare bottleneck and the limits of deep learning. When we look at traditional deep learning, it's essentially a brute force approach. It's wildly data hungry, requiring millions of perfectly labeled examples, and as we just established, it acts as a total black box. But there's an alternative, a really clever underdog solution called domain knowledge AI. Because this approach is guided by human experts, it's structurally designed to prioritize the exact same features a human doctor would look at. And the result? It doesn't just get more accurate with less data. It becomes highly interpretable. Moving on to Section 2, how doctors actually read heartbeats. To build a smarter AI, we really have to understand the specific architecture of a heartbeat, the classic electrocardiogram or ECG wave cycle. Think about the key landmarks here, P, Q, R, S, and T. Cardiologists spend years training to read this exact skeleton. The P wave is the upper chambers contracting. The QRS complex, that's the main pumping of the lower chambers, and the T wave is the heart resetting itself. A seasoned doctor doesn't just stare at a messy, squiggly line. They're looking for the relationships, the distances, and the shapes of these specific PQRST landmarks. So, the crucial piece of the puzzle is how we define this expertise. In the context of our explainer today, domain knowledge is the accumulated, validated expertise of human specialists. It includes the specific anatomical regions they focus on, like that powerful QRS complex, and the characteristics they prioritize. The goal of the researchers here was brilliant. Let's translate this wealth of human experience into a structural mathematical map that a machine can actually process. Section 3. The graph network solution. Now, before the AI even begins to analyze the rhythm, it has to clean up the raw data. Think of it kind of like a surgeon prepping a sterile operating room. First, they apply a bandpass filter to suppress background noise, stuff like muscle twitches or even power line interference. Second, they use a nonlinear transformation to specifically enhance those crucial QRS pumping complexes we talked about. And third, they bring in a mathematical technique called a dyadic wavelet transform. It basically acts as a precision tool to automatically extract the exact locations of the P, Q, R, S, and T points. So before the neural network even wakes up, the data has been expertly curated to highlight the exact domain knowledge a cardiologist cares about. All right, Section 4, spatial and temporal streams. This is where the mechanics get really cool because it brilliantly illustrates how the AI mirrors human thinking. We have two distinct streams here. The spatial stream looks at a single heartbeat, an intra-cycle connection. It draws a directed path from P to Q to R to S to T. It's analyzing the physical shape of one single pump of the heart. But as you know, a cardiologist doesn't just look at one beat. They look at the rhythm between the beats. That is where the temporal stream comes in. This inter-cycle connection draws a line from the P wave of beat 1 directly to the P wave of beat 2, tracking how the rhythm evolves over time. So you've got shape on one hand and rhythm on the other. Put all of that together and you get the complete architecture of the double-stream directed graph neural network. Let's trace the flow really quick. The raw ECG sequence comes in, it gets pre-processed to find those key points, and then it splits into our two streams. The spatial stream analyzes the shape of individual beats, while the temporal stream analyzes the rhythm across multiple beats. Finally, these two streams concatenate, they join back together to output a highly accurate unified diagnosis. It's honestly just a beautiful synergy of human anatomical knowledge and raw machine processing power. Section 5. Smarter Rare Disease Detection. Let's look at the hard data. When we compare F1 scores, which is a measure of accuracy that considers both precision and recall, against previous state-of-the-art AI models, the results are pretty undeniable. This new domain knowledge-guided method consistently beats out the competition, hitting an overall average F1 score of 88.1%. By actually teaching the AI what to look for, rather than just letting it guess from a sea of pixels, the accuracy just jumps significantly across the board. But honestly, this is the number I really want you to take away: 76.3%. This is the F1 score for detecting rare categories, specifically left anterior fascicular block and early repolarization. In traditional AI, because these conditions are so rare, there just isn't enough training data, and accuracy completely plummets. Previous models were scoring down in the low 70s. But because this new model is guided by the fundamental rules of cardiology, it can accurately identify these rare anomalies even with super scarce data. That is a massive leap forward for rare disease detection. Finally, Section 6. The future of transparent AI and building trust. Because this AI is built fundamentally on the PQRST framework, it doesn't just output a vague probability score of a disease. It actually plots out the key points it used to make its decision right there on the monitor. Even with noise and baseline drift messing with the signal, the AI correctly identifies the landmarks. For a doctor, that black box mystery is completely gone. They can look at the screen, see the exact P and T waves the AI flagged, and instantly verify if the machine's logic lines up with their own medical training. As the researchers so perfectly put it, trust comes from understanding of how decisions are made and what are the determinants of these decisions. Fusing domain knowledge with AI doesn't just improve the math. It creates a transparent, collaborative system. It literally turns the AI from a mysterious, unexplainable oracle into a trusted medical colleague that can actually show its work. We've seen how powerful this is in cardiology. By simply teaching a neural network the basic skeleton of a human heartbeat, we unlocked higher accuracy, vastly better rare disease detection, and total transparency. So I'll leave you with this thought to chew on. What other industries out there could be completely transformed if we stop trying to replace human knowledge with raw data and start actively fusing it with AI? Thank you so much for joining me for this explainer. I really hope this sparks some new ideas for you. Keep learning, and I'll see you next time.